Hello, this paper is called Redwood, Using Collision Detection to Grow a Large-Scale Intent Classification Dataset. My name is Stefan Larson, and this is work with my advisor, Kevin Leach, and we're from Vanderbilt University. Where this paper fits within the broader context is within the fields of task-oriented dialogue systems and intent classification. This paper investigates the task of intent collision detection where two intent categories from different source datasets overlap. We then use intent collision detection to safely merge 13 different datasets into a single intent classification dataset. This end result we call Redwood, which consists of 451 unique intents. And this is a new staple for investigating large, robust intent classification models. First, let's talk about the problem of intent collision detection. During the development of a task-oriented dialogue system, multiple people or teams may add intents over the lifespan of the system. In industry in particular, this can go on for many years. As an example, let's say that Team A adds a get weather intent to the first iteration of System A, and then years go by, and then Team B inherits the project and wants to merge System A with their dialog system. And their dialog system also has a similar intent for handling weather-related queries, but it's not named get weather. If Team B doesn't realize that these two intents overlap, then this could cause the system to exhibit unexpected behavior. Now for some real-life examples of colliding intents. First, here are three samples from the SNPs dataset. These are all weather-related samples. Here are three more samples from the Clink 150 dataset. These are also weather-related samples. You can see that there's similar overlap. And then finally, here's three more samples from the MTOP dataset. So we can see that each of these datasets have a weather-style intent, and we would consider these colliding intents. Similarly, three more data sets all have an alarm style query, and they might also have an exchange rate query, exchange rate intent as well. In this paper, we introduced two different methods for detecting colliding intents. The first one we call classifier confusion. Here we consider an intent X in dataset C, and if we train a classifier on that dataset C, and then we test on a new intent Y, then if a large amount of data in intent Y is classified as intent X, then we say that there's potential for a collision between X and Y. And the way we predict a collision is we use a threshold on the proportion of the samples in Y classified as X as a way of predicting if there's a collision or not. The second method is what we call data coverage. In this method, we say that intent X collides with intent Y if some distance measure between X and Y is less than a threshold. In our implementation, however, we use a metric called coverage. So coverage of X on Y or over Y. We say if that's above a certain threshold, then there is a collision. The specific details of these two methods are in section 3.3 of the paper, but importantly, both methods yield a value which can be mapped to the real line, and larger values mean a collision is more likely. And for this reason, we can use AUC score to measure the discriminability between collision pairs and non-collision pairs. To measure the performance of the intent collision detection methods, we curated a metadata set of collisions. These are from 13 individual intent classification datasets. They're shown at right here. And we found that there were a total of 570 collisions. Now onto some results. For the classifier confusion method, we trained a SVM as our classifier on TF-IDF features. And we find that this particular model type and this method type doesn't do too well at detecting collisions. We see that the AUC score is pretty mediocre. There are indeed a lot of overlap. There's a lot of overlap between colliding and non-colliding intent pairs. Next, the data coverage method. We're using SBERT mini LM as our features. Here we can see that this method is a lot more capable of detecting intent collisions. Now on to constructing Redwood. We use our intent collision detection methods to help us construct Redwood. We also use human in the loop to make sure that these are actually colliding intents. So we use our collision detection and we end up with 451 unique intents. This is after merging colliding intents, of course. And importantly, we don't include intents that cause non-transitive relations. This shows an example of a non-transitive relation where intent X has overlap with Y and Z, but Y and Z are not collision pairs themselves. What we would do, we would just discard intent X. And the source data sets are the same as before. We evaluate a mobile BERT model on Redwood. We evaluate in-scope accuracy, and then we have 2 held out data sets for measuring out-of-scope performance. We find that the mobile BERT model on Redwood does perform quite well, and similarly for out-of-scope tasks. And then we compare this model to one trained on what we call Redwood naive. Redwood naive was formed by naively joining together intents without arbitrating collisions. We find that this model performs worse than when we do actually arbitrate collisions. In conclusion, intent collisions can occur when developing large task-oriented dialog systems, and they can cause problems if not addressed. We introduced 2 methods for detecting intent collisions, and then we use these 2 methods to help us create a new dataset called Redwood, which is a large-scale intent classification dataset. Dataset can be found on GitHub. Thank you.